Hello everyone, this is lecture 5, ECE350. In this lecture, we're going to talk about lossless transmission line and also reflection coefficient. Let me draw a transmission line over here and try to see what you mean by lossless. So transmission line, you have seen that it has these parameters, right? This is a section of the transmission line. So this is the R prime here, L prime here, and R prime, L prime here. This is again is Z prime here and C prime here. So lossless means there should not be any loss for the signal going through it. That means there should not be any R, and also there should not be any conduction between these two sections of the line. That means your Z should be also zero. So that lossless means that your R prime and G prime should be zero. That means lossless. So, and also you have seen that propagation constant, this equation over here. For the lossless line now, if you have R prime and G prime are zero, then your real part is zero for gamma. So that means you only have your imaginary part, who is the phase constant. So there is no attenuation. So your signal over the line, let's say if a distance over here x, and your signal is here, signal would be same over all distance. There is no attenuation because of alpha is 0, and there could be a phase difference between at different point when you have the look at the reference time. So also your characteristic impedance come to this one here. You know what is that? This is basically R plus j omega L prime over Z prime plus j omega C, right? So C prime. So if we take this one 0, that becomes this one here. So this is the characteristic impedance for a lossless line. So it changes for lossless line, both equation for characteristic impedance and also propagation constant. So now, if you go back here for lossless line, these two are 0, right? Then if you modify the equation for lossless line, your phase velocity, how fast your signal traveling through the line, it becomes this here. And you know what is the mu is permeability. It's a property of materials for magnetic field, and epsilon is permittivity. That's also property of materials for electrical signal. So it now depends on materials property. So how fast your signal going, that depends on materials property mu and epsilon. And same here, your beta also depends on materials properties now mu and epsilon, right? Let's go forward and see what else there. So now, if we go further down the road, for conductor and dielectric materials, mu r, which is called, what is mu r here? Your mu is basically mu 0, and your epsilon, actually epsilon r, epsilon 0. What is epsilon and mu 0? These are the respective value for vacuum, right? So it comes down to epsilon r, C over epsilon r. So your phase velocity, your phase velocity or velocity of a wave, it can go as high as speed of light if mu r is 1, right? That's one here. And also your lambda, the wavelength of the signal, depends on mu 0 over epsilon r. And what is lambda? Lambda is basically C over F, right? So now, if you look at this equation over here, you can see that if your materials, property does not depend on frequency, if this one does not change with the frequency, because in your transmission line, you're trying to send a frequency with different signal with different frequency, right? So if your epsilon r is not dependent on frequency, then your phase velocity does not depend on frequency. That means all the signals going through the transmission line will go at the same speed. That means you don't have any dispersion in the line. Make sense? So when you select materials for the transmission line, you do not select them just for mechanical strength. I'm talking about dielectric materials around the conductor. You also consider electrical property like epsilon r. That should not be depending on frequency. If it does not depend on frequency, then all the signal going through that transmission line would be going at the same speed. So it does mean you're basically sending some pulse, right? Each of the pulse is made out of infinite amount of sinusoidal signal, right? So that means each pulse contains a lot of signal with different frequencies. Now, when pulse go through the transmission line, that pulse should not be dispersing because all the signal should be going at the same speed if your dielectric materials in the transmission line does not depend on frequency. All right. Now, that's what I'm saying over here. So you can take a look what I said. That's all about that. Your epsilon r should not be depending on the frequency. And for general case and other things, you can see for all the signals. This is the equation for your proportion constants. This is the phase velocity over here. This is the characteristic impedance. And if you have a lossless line right here, that equation changes. For the lossless coaxial, equation changes a little bit, and so on, right? So this is the chart over here for the parameters for different type of transmission line, and also how to find them in the equations, right? So I'm going to do the same problem here in the class. We're gonna apply what we have learned here into the problem in the class. All right. So now we're going to talk about the voltage reflection coefficient. We have seen the lossless line, and we have seen how you can design a line to be non-dispersive. And now we're going to how to find the reflection coefficient, right? Because we know that when incident when it goes to this way, some of them reflect back, right? So how much is reflecting back? It depends on reflection coefficient. So over here, it has two parts, right? Incident and deflection, and same here, incident and deflection, right? So at the load end over here, we start all the measurement. Remember, we start all the measurement from the load end. So Z0 over here, then you will find this equation over here, and also you'll find this equation for the current if you put Z equal to 0 into the previous equation, right? And this one over here is I0 plus is V0 plus Z0. That's your impedance, characteristic impedance. And again, I0 minus, which is reflected part of the signal, is V0 minus over Z0, right? So now if you now say that ZL would be VL over IL, right? So if I do from here, if I bring it down here, ZL is VL over IL, and if we put it back here, your equation would look like this, right? Right? So now, what is the reflection coefficient? Reflection coefficient is a signal reflected back divided by signal going towards the load. So the incident signal here and reflected signal here. The ratio is the reflection coefficient, which is a big gamma, right? So reflection coefficient, if you do the math over here and basically rearrange this equation over here, it becomes this. So what is that? Reflection coefficient is ZL, load impedance minus Z0 over load impedance plus Z0. Or you can normalize them, dividing all the component by Z0. You normalize them, so it's a normalized one right here. All right, this is a normalized value. So now, if you look at here, you can see that if your let's come back over here. If your ZL, Z0 is your characteristic impedance, right? So if you load and the characteristic impedance of the line, Z0 is the characteristic impedance of the line, if they're both equal to each other. So you have a load that's same as your characteristic impedance. Look at what's happening here. ZL equal to Z0, then your reflection coefficient becomes 0. That's the ideal case. So nothing is reflecting back from the load. So you're sending a signal from one antenna, another antenna is receiving it. So if it's not reflecting back from the other antenna, the other antenna receiving all the signal you're sending. That's the ideal case. That only happen if your characteristic impedance equal to your load impedance. There's a goal here, and I'm gonna see in the end of this chapter is that how to make that happen. Because your transmission line coming into a load and transmission line doesn't match each other, so we have to do something to match them. We're gonna see them at the end of the chapter. All right. So here's a few things over here. So this is the load, right? This is the reflection coefficient magnitude, and this is the reflection coefficient angle, right? It's called reflection coefficient angle theta r. So it's basically you're taking the cosine value, sorry, tan inverse value of the uh, numerator and subtracting the denominator from that. That's the value over here, right? So your r and x, those are all your normalized value of r, normalized value of x. All right. All right. Now it's a general case, right? If they're matched to each other, look at here. So there's no reflection, right? Then your angle is irrelevant. And if we short circuit here, short circuit, right? I'm gonna put this equation back here again so you can see it. ZL minus Z0, GL plus Z0, right? That's the reflection coefficient angle, right? So the magnitude. So short circuit means your ZL is 0, right? So if ZL is 0, then if you look at the magnitude over here, the magnitude becomes 1, right? This is 0, this is 0, so magnitude becomes 1. And your phase angle becomes plus or minus 180 degree. Okay, so we ZL is 0, right? So ZL is 0, your phase angle becomes, if you look at here, your phase angle, if you do the math over here, phase angle becomes 1 plus minus 180. Open circuit, that means your ZL is infinity, right? Or very large. For this purpose, it's very, very large. If it's very, very large, this one also becomes 1, right? So GL is really, really large, so G0 doesn't matter. Then also becomes 1, and your angle become in phase. We're going to talk about them, how it's become in phase in the next few chapters. And if you have, let's say you have your ZL is now 100% inductive. If your ZL is 100% inductive, that in that case you also get this one is what do you call it? 1. How does it happen? How does that happen? If it's 100% inductive, then if you take the magnitude of both sides over here, all right, that also becomes basically fully 1. Let's do a math over here. So as you know that your Z0 over here is for lossless transmission line is just a real number, right? So let's say that is 10, right? G0 is 10. So let's say negative 10. Then you have J plus J omega L. Let's put it 50, right? So J, right? Okay. Then over here you have J omega J50 plus 10, right? So if you take the magnitude now here, look at what happened. If you take the magnitude doesn't care what sign it is. So it's 10 squared plus 50 squared. Then same here, 10 squared plus 50 squared, right? So it's become 1. That's what I'm saying. So that means if you have a purely inductive or purely capacitive, your reflection coefficient is 1, 2. So look at that. All those things will give you 100% reflection, which is not a good sign, which is not good. So your load is not receiving anything, reflecting back everything. And more of that we're gonna explore them in the class, why angle happens. All right. So I'm gonna stop here, and we're gonna go to the next part in the next video.